Hello everyone, my name is Lu Hao. I'm from NXP Semiconductors. My job is to develop the random test case generation tool for NXP's RISC-V processor verification. Today I'm going to present how we use the random test case generation tool to verify the debug unit for a RISC-V processor core. Here is an overview of what I'm going to talk about today. First, I'll show a diagram of the DUT. Then I'll talk about verification challenges and how we resolved it by using the random test case generation tool. Then I'll go into details about our verification methodology, including debug verification environment, verification targets, and debug checkers. Last, I'll talk about the results and coverage. This slide shows a diagram of our design under test. We have a CPU, which is a RISC-V processor. It's connected by the debug module, which includes debug registers and debug CSRs. There's also a trigger module, which contains the trigger CSRs. Our goal is to verify both the trigger module and the debug module. The CPU can be debugged from the very first instruction. The debug module contains the run control functionalities such as halt, resume, and single step. It can halt the core whenever there's a hit on the software breakpoint or trigger matches the program counter or read-write address. It can do single-step instruction execution. It can request the system to reset the core. The abstract commands can control the program buffer execution or directly read-write to the general-purpose registers. When the core is halted, the instructions placed in the program buffer can be triggered and executed via abstract command to achieve the purpose of accessing system memory or modifying register data. Unlike some other implementations where the program buffer uses the processor memory space, our program buffer is physically located inside the RISC-V debug module. The verification challenges are similar for both implementations. Our verification challenges include, first, putting the core in different configurations or situations. In reality, external stimuli such as interrupts or debug exceptions could happen anytime during course execution. User could request debug at any time under any core state. We want to cover such kind of random cases as much as possible. Second, we want to exercise random instruction stream in debug mode session with varying debug control configurations. Last, the correctness checking is a challenge. The interrupts and debug requests are all asynchronous events, and we want to synchronize them between the RTL and the functional model to better compare the results. Also, the register and memory values will change after the interrupt or debug request is finished. We want to have the correct set of the expectation of the updated register and memory data. To overcome the above challenges, we introduced the random test case generation tool called Raptor in our verification environment. Raptor supports user-controlled randomness via a specific C-like language, where user can write control flow structures such as if-else or while loop. It also supports querying generator or processor state during runtime, so that user can use the value of register X5 after the 10th instruction execution to determine if the next instruction to generate should be a jump or a subtraction. User can apply various controls to constrain the instruction generation, such as limiting all load or store access within an address range, or never write certain bits to 1 in a CSR register. These will constrain Raptor to choose only valid source registers or assign valid immediate values to certain instruction operands. Raptor also supports randomly inserting various types of events during the test case generation, such as various debug requests and triggers. The verification environment parses the events and generates the same ones for the test bench. One problem is that the events are asynchronized, which means once inserted in the RTL simulation, it might not be happening at the exact same timestamp as in Raptor. If the state of the processor is modified during the events, the rest of the test would be heading different directions between the Raptor test case and the RTL simulation. The next few slides will be talking about how we handle this situation. Here is a diagram of Raptor test case generator. Raptor takes the macro file as the input. In this file, the user can write different types of biases and constraints to control how Raptor generates the random test case. Then the macro file is sent to the Raptor engine to go through the following process. First is the syntax checking to make sure there's no syntax error in Raptor language. Then the constraint solver will resolve both the architectural constraints and the user constraints in the input file. Then Raptor starts to choose valid resources and assign operands, and the opcode will be generated. Then the opcode will be sent to the reference model and execute. The output UVP file will contain the instructions and the execution results. Next, I'm going to give more details on our verification methodology. First, I'll show you the debug verification environment. Next, we'll look into our 3 verification targets: run control and external triggers, data and instruction triggers, abstract command, and program buffer execution. Last, I'll talk about debug checkers. The debug verification environment is a 3-stage process. In the pre-simulation stage, we use Raptor to generate random test cases. In this step, the user writes a Raptor macro file to give constraints and biases to the random test cases. Raptor then reads the macro file as an input, generating the test cases, and run a functional model to simulate the execution and generate the results in the UVP file. The UVP file is basically a text file. It contains the register and memory initialization values, the instructions being generated, the intermediate results after executing each instruction, and the final results after executing the entire test case. During the simulation stage, the UVP file is being parsed. All the register and memory data parsed from the UVP are loaded into the simulation environment, and the RTL runs based on those preset values and generates the RTL trace. The RTL simulation will also generate an event file, which contains the trace of all events such as interrupts and debug requests. In the post-simulation stage, the events file and the UVP file will be combined and put into the functional model again to generate a model trace. This model trace will then be compared with the RTL trace, to get the final results. One of our verification targets is to verify run control and external triggers. For example, the core should be able to respond correctly under varying configurations if we issue a halt or an external trigger from the debug module. We have developed a debug environment test bench to randomly issue debug requests or external triggers during core's execution. These are issued during the active mode. When the core finishes its task in the debug mode, the passive mode will be invoked to issue a resume command if core enters debug mode due to internally generated events like breakpoints. Our next verification target is to verify data and instruction triggers. The core should be able to enter debug mode or be able to service debug exceptions correctly when certain load or store address or certain instruction address is hit by a trigger. In reality, the trigger could happen to any address under any circumstances or core configurations. In Raptor, we implemented the following macro functions to achieve invoking triggers during random time and under random core status. For issuing random instruction triggers, we pre-configure trigger data register tdata2 to a random address, but still within the instruction memory space. Then we configure trigger configuration register tdata1 to a random combination of type, dmode, and data. Then we call a long series of random instructions to cross the trigger address so that the trigger will be invoked. For issuing random data triggers, we again use the same way to configure tdata2 and tdata1, but within a certain data memory region. Then we call a series of load or store instructions combined with any type of instructions to hit the trigger address. Our last verification target is the abstract command and program buffer execution. By configuring the debug register called command, the user can perform different types of debug operations to the CPU, such as read, write to a register, or execute instructions in the program buffer. One problem we met is that executing an abstract command can potentially alter core's context, such as CSR or GPR register value change, or change to a different privilege level. Because of this, the core can potentially deviate from the intended programming region. The first leg of our solution involved enhancing Raptor and creating a random stream of instructions in both run mode and debug mode. Second leg involved developing test bench to precisely put the core in debug mode right where Raptor embedded the debug mode instructions statically. Since the debug request in the RTL simulation can take several cycles to become effective, this will cause the RTL simulation result deviated from the Raptor result after the debug request is completed. To overcome this, we introduced the save restore mechanism, which is to save the core's context when the core hits the debug request point. Then issue the debug request. Once the core halted and entered the debug mode, which was already several cycles later, the core's contexts are restored to the point that happened several cycles ago. When programming the program buffer, the user can use the following macro functions in Raptor. The user can either write a direct opcode to one of the program buffer register or ask Raptor to generate a random instruction with different types of user constraints. The user can also configure all the program buffer registers all at once by simply call one macro function. We have developed the debug checkers to do exhaustive checking of signal level protocol that are not always traceable, such as CPU and debug interactions, debug state transitions, external notification on the output port for non-debug trigger actions, number of steps during single stepping. Any change on the input port of the debug module are captured and pushed back in the internal queues. For any transition in debug state or on output boundary, the relevant queue is popped and mapped back to the source of impact. If no credible source is found, an error is flagged. At the end of the simulation, all internal queues are checked if they are empty, or else flags an error, citing that few transitions remain unexplained without an impact. By applying the random test case generation and verification methodology, we were able to achieve 100% functional coverage of the debug module and 100% code coverage with the help of UNR analysis. We have also found multiple corner case bugs and hit several complex scenarios that could be hard to simulate by using conventional directed verification. By using the random instruction and event generation method, we could generate instructions in program buffer that executed in different privilege modes, debug features crossed with other features such as interrupts, decode class exceptions, and also we generated the scenario that external debug happening during the internal debug session. Those are valuable in scenarios that helped us find several corner case bugs. Here is a diagram of the weekly program buffer instruction coverage. For the first 4 weeks, we primarily ran directed regression suite and were able to achieve 35% coverage. The Raptor random test case generator tool were also being developed during this time frame. Then we took 5 weeks to run Raptor and generated a huge amount of different scenarios. This helped us increase the coverage to 99%. In the end, we spent 6 weeks fixing random test case generator bugs and 2 issues, doing exclusion and closure, and finally achieved 100% coverage.